Last time we talked about until section 4.1. Today we continue from 4.2. Okay. So here is we look at the single most important internet protocol, which is IP, Internet Protocol. Here we want to look at the addressing, subnetting, forwarding, packet format, and reassembly, fragmentation and reassembly. IP address addressing, it's a globally unique 32-bit address, and it's hierarchical, unlike a MAC address, which is flat, essentially flat. Here it's hierarchical, and consists of network ID and host ID, or network address and host address, or you can call a network number and host number. So two parts in the address. So it breaks down the address into two parts. And when it does routing, it only look at the network part, the network address, network number. It does not look at the host number. So that makes it more scalable, which we have just explained. You don't have to look at the entire address to handle so many numbers, so many addresses. You only handle the number of networks. In doing routing, you don't need to face a number of networks, not a number of hosts. A router usually has more than one interface, so it has more than one address. And a host usually has only one address, but it could have more than one. If you have more than one address on a host, suppose I have only one interface card on the host, but I have two addresses on the interface card, two IP addresses. Then we call it's a IP alias. So you alias the other IP address onto the same interface. That's called IP alias. If you have this. Okay, so here's a IP address notation. And we also explained that because this IP address is 4-byte data, multiple byte data. And when you have a data which is multiple byte, you need to be careful in the order they are stored in the memory and the order they are transmitted. And it could be big endian or little endian. So for the 4-byte IP address to be stored in a big endian machine, it will be stored in a way like this. The high order byte, this is the high order byte stored in the low order address. The low order byte stored in the high order address. And that's big endian. That's when it's stored in the memory. And when it's transmitted to the network, you need to consider the byte order and also the bit order. And the byte order is about the order that the network layer passed the byte through the link layer. If it's a big endian byte order, it will pass the high order byte first. So you pass this one, and then this one, and then this, and then this. So you pass the high order byte first through the link layer from the IP layer, from the network layer. And IP says in the IP layer say it's big endian. So from IP layer passing through the Ethernet or wireless LAN, it passed the high order byte first. Okay. How about the bit order? The bit order, If it's a little big endian, then you transmit from the high order bit first. But if it's a little endian, then you transmit from the low order bit first. And Ethernet is big and little endian, so you transmit from the low order bit first. And we have explained this in chapter 1 and chapter 1 or chapter 2. Okay, the address of 32-bit long, it will be a space of 4 billion hosts. 4 billion addresses. You got 4 billion addresses. And it's divided into class A, B, C, D, E. And class A is a few networks. Each of them is very huge with a 3-byte host number. However, for class B, the network is also big, but not that big. With each network having 65,000, about 65,000 host addresses. Okay, that's for class B. And class C is a large number of tiny network, small networks. So you got a lot of such class C networks, but each will be small with a host with just 1 byte host number. With just 256 hosts within each network. And class C is not assigned to a particular host. You don't assign class D to a particular host. You use class D as multicast address. So it will represent a group of hosts, not a host, but a group of hosts. That's for class D. And class E is reserved for future use. Okay. But again, for class D and E, they are not big. They are not that big. Okay, so we are using A and B and C. And according to ICANN, it has no free class A and B to allocate, but it still has class C, and it claims that it's exhausting the allocation of class C. Okay, so many NIC and IC, for example, in Asia Pacific, it's called AP NIC, have been exhausting the class C allocations, so they are running out. But again, they allocate not to individual user. They allocate the address space to the so-called ISP, Internet Service Provider. So the internet, even though ICANN or NIC do not have for more space to allocate, the Internet Service Provider they have a stock of address space that could be allocated to individual users. So this year, no further ISP can get more address block from the NIC, but they still have some address to allocate to individual enterprise or user. And it is expected that depending on which country, some of them will have more to allocate, but some would not have. But for those ISP who does not have address to allocate, what happened? What would they do? They would allocate private IP address, which we will see later. There's a segment, 3 special segments of IP addresses, which are reserved as private IP addresses, and they shouldn't appear in the public internet. They should be only used internally in an intranet, not internet, and we will see that. And there are some special IP addresses, like if the host ID is 0, then it's denoting the network itself. If the host ID is 01, then it's a broadcast address of the network. And the subnet, okay, so the subnet is the same as VLAN, or so we say that a broadcast domain, if it's defined in the link layer, it's called LAN or VLAN, physical LAN or virtual LAN in link layer. But if a broadcast domain is defined in the network layer, then we call it subnet. So they are essentially the same concept, broadcast domain, but defined at 2 different layers. So subnet, by definition, is a broadcast domain at the network layer. So essentially, I'm grouping the host into the same broadcast domain, which will form a subnet. And I would use a subnet mask to identify a subnet, okay, to identify the network address of the subnet. And hosts within the same subnet would talk to each other without intervening the router. So since they share, they are in the same broadcast domain, they can talk to each other directly. They can send broadcast frame. Okay, so that's the idea. But if you want to talk to some host which is not within the same subnet, then you would need the help. You would need the help of the router. So you pass the packet to the router, so that the router will forward the packet for you. Okay. Okay, and so, for example, this is the IP address in Zhongzheng University. It has a subnet mask of this. So this is a host with a subnet mask of this. It says that it's 01 for the first 3 bytes. For the first 3 bytes. And okay. And or you can represent it in this way with an IP address /24. The number of 24 here means the length of subnet mask. The length of subnet mask. In this case, is 24 bits or 3 bytes. So you would do partition within class A. You do partition. Class B, you do partition. Even in class C, you can partition too. So you have only 8-bit host number, but you could further divide it into a subnet. So you can use say 4-bit as subnet network address, and the other 4-bit as host number. So you can divide them, and this is just one example that you can divide it into different subnets. But if I need more subnet, then I can use more bits for the subnet. If I need to divide it into less subnet, then I can use less bit to represent subnet number. So the boundary can be adjusted. I mean, the number of bits you use for subnet and host could be adjusted. Okay, here's an example of you got 1, 2, 3, 4 subnets in this network. 4 subnets connected by 3 routers. So here you see the network address of this subnet, and also you see the IP address of each host and router. and of course, because the router has 2 interfaces, so it would have more than one IP addresses. So you got 2 IP addresses. And these 2 IP addresses are on different subnets. So I'm a host. I'm crossing on 2 subnets. On this arm, on this side, I'm connected to 1 subnet. On this interface, I'm connected to the other subnet. Okay. Originally, they were dividing subnet like this, with a fixed number of subnet address, and fixed number of host address. But later on, they realized that it would be a problem for Class C. Every time we allocate a Class B address, we would increase the number of routing table entries worldwide in the backbone router. Every time we do that. So that's okay for Class A and Class B, because the number of network or the number of subnet in the number of network in Class A and Class B are not too big. So we can every time we allocate a new subnet, a Class B network to an ISP, we increase a routing table entry worldwide in a backbone router. Suppose they are 100,000 routers, backbone routers, 100,000. Then each of them would have one more table entry to keep track of that particular Class B network. Okay, so everyone needs to keep one more entry in their routing table, which is fine. But when they start to allocate Class C, it is a problem. Every time we allocate a Class C address, we increase a routing table entry, which is bad because we have so many Class C networks. Each of them will be tiny, small, but we have got so many Class C. So they don't want to do that. They say it's a scalability problem. Too many Class C routing entries. Too many routing entries for Class C networks. So what we want to do is that we want to have an arbitrary length of network address. Okay. So we denote it by this /x, meaning the length of the network. So to which bit, how many? If it's 24, then it means 24. The first 24 bits are network address, while the remaining bits are host address. And it's adjustable. It could be 24, 25, 26. Okay. So when we allocate Class C networks, what the NIC wants to do is they would allocate consecutive Class C together. Say, I give you a 16 Class C address, Class C networks. So it'll be a consecutive blocks. And when I allocate this to you, 16 Class C networks, but it would only increase 1 routing table entries worldwide in the backbone router. Instead of 16 routing table entries, now I got only 1 new entry in the backbone routers. So what we want to do is we want to treat these Class C together, 16, as 1 address space instead of 16 address spaces. Okay. So that would not increase the routing table entry so fast. The routing table entry would not increase so fast worldwide in the backbone routers. And the idea of doing this is called classless IP address, in a sense that it tells that you don't care much about Class C, Class B, Class A. You treat one chunk of address space as 1 entity, and would only increase 1 routing table entry in the backbone routers. And ICANN is the organization that allocate address and also manage domain names. Okay. And so we look at if we have a packet coming in, if we receive a packet, then we need to forward a packet. And the forwarding could be through the upper layer or through another network interface. So either go up or go down. Go up or go down. And to forward that packet, if it's go down to the interface, another interface, then it's based on the routing table entry. We need to look up the routing table. And the routing table should have the destination network represented by the address slash the subnet mask length, and then next hop, the next hop router. So essentially, each routing table entry tells to this network, you should forward the packet to this hop. Well, this hop usually is another router. And however, that's on a network, on a router, but on the host, you only need to know who your default router is. So I would have this entry in a host saying, okay, my default router is this one. So every time when I have a packet with a destination not within the same subnet as the destination is not in the same subnet as I am in now, I will send a packet to the default router. And the default router should handle the rest. So, here's what you do is at a host. At a host, you have a packet. What you want to do is that you want to check the destination IP address of the packet to see and then see the network address to see if the destination is in the network. The network of the destination is the same as my subnet address. So if this is the same, then it means that we are in the same subnet. And when we are in the same subnet, I can send a packet to the destination without intervening the router. So I would send a packet directly to the destination. But if it's not the same, that means we are not in the same subnet. Then I would look up the routing table to find my default router and then send a packet to the default router. However, in order to check whether the destination is in my subnet, or I misspell it, in my subnet, then what we want to do is this. We take the destination address of the packet and with my name mask, subnet mask. And then I also take my own IP address. This is the destination IP address of the packet I'm handling, and this is the IP address of myself. And here I take my own IP address and with my name mask. So I got my network address, and also I got possibly the destination network address. And I do what? Exclusive OR. This is exclusive OR. I do exclusive OR on these two network addresses. So when we write this, essentially you are doing this. You do this and this and this, and then this and this. So you got two entries, and then two do exclusive OR. Or alternatively, you can do exclusive OR first, and then do AND. They'll be the same. The result will be the same. You either do AND first, and then exclusive OR. Or you do exclusive OR first, and then do AND. It'll be the same. But essentially, the original meaning is that we want to do is end first, to end. I take the destination IP address of the packet to end with my subnet mask, and then I take my own IP address to end with my own subnet. So I should got the network address, right? And then I compare them, and the way I compare them is to do exclusive OR. If they are the same, the exclusive OR result will be what? 0, right? Will be 0. If they are not the same, then the exclusive OR result will render non-zero value. It will be non-zero. But in this formula, it does exclusive OR first, and then do end. But the result will be the same. So I'm checking whether the destination is in my subnet. If it is, then I send the packet to the destination directly. There's a detail here that because we haven't touched about ARP, but we'll see it today. That you know that this network, you got a packet, and you take the destination IP address and do this, and then you find that this destination IP address is in the same subnet. Then you want to send the packet to the destination directly, but you need what? The MAC address because you need to pass the packet to the link layer, and then link layer transmit the packet. So you need the MAC address of the destination, but you only got the IP address of the destination. So what you want to do is that you issue a protocol message called ARP, Address Resolution Protocol, asking it's a broadcast frame on the subnet, asking who has this IP address. If you have this IP address, send me your MAC address. So you got ARP reply from the destination because you broadcast this ARP request on the subnet. So the destination will get it because it is in the same subnet as you. So it will get it and then send an ARP reply by unicast. And then you got the MAC address of the destination. Then you will be able to fill up the MAC address, destination MAC address in the link layer, and then send the packet out. Okay. How about in the router? In the router, you need to look up the routing table, and the packet might be going up to the upper layer or going down. And for going down, it would have two scenarios the same, that the destination is in the same subnet. Then you can transmit the packet directly to the destination. Another case will be the destination is not in the same subnet. Then you will send it to the next hop router. Okay. And in most cases, it will be this. In most cases, you'll be sending to the next hop router until you reach the destination subnet. Then it'll be this case. So you would say the packet would traverse 10 hops. So you would traverse 10 routers, and in the 10th router, you will see, okay, the destination is on the subnet of this site. So I can send the packet to the destination directly. And when we are looking at the routing table, in order to find the next hop, there might be duplicate matches. And here's a scenario that you have a duplicate matches. Suppose I have an IP address space allocating to class A. However, I also allocate class to class B, and these two space is kind of overlapping. That this space is to A, but I grab a small portion to B. Then what happened is, this is exactly what happened here. In class A, this space is actually covered here. This space is actually covered within this space. And so it would introduce duplicate matches when you do a routing table lookup. For example, I have a packet destined to this. And by your bare eyes, you know that this address belongs to whom? Belongs to B, right? But the computer does not know. It will say, okay, this address belongs to A and also belongs to B. This belongs to A and also B. So when you take this to match the routing table, you will have two matches. One is this entry, and the other will be this entry. Two matches. Both entries will match. It will, or I would say, this address will match both entries in the routing table, but this will have a 21-bit match. I mean, the match will be 21 bits long, but this match will be 24 bits long. And we say that you should pick the longest match. When you have duplicate matches, you pick the longest one. So that should be the longest, the right routing entry you would use. But that's from, so you pick the longest one. That's how you tell the program to do. By your bare eyes, you know it belongs to class B, but for the computer to run, it is essentially a longest match, longest prefix match. And that's because of this scenario. You have this. When you have this kind of allocation, you would have duplicate matches. And we will see how Linux do longest prefix matching in the kernel. Okay, here it's an open source implementation for packet forwarding, essentially to look up the routing table. And within Linux kernel, the routing table is organized into two tables. One is called routing cache, and one is called routing table, which is all called FIB, forwarding information base, FIB. So you search. The idea is that you search the cache first. If not found, then you search the FIB. So here you search here. You search the cache, and if found, if cache hit, then done. If cache miss, then you do this, and this is slow. It's going to be slower because you are looking at a large table, FIB. And let's look at the cache first. Essentially, both tables, the cache, routing cache, and FIB are both implemented in hash table as hash tables. However, the routing cache is just a simple hash table, but the FIB table is an array of hash tables. It's not just one hash table, but an array of hash tables. But let's look at the routing cache first. So you take the IP address. So essentially, you take the IP address, destination IP address of the packet to forward, and then input into a hash function. And the hash function will generate a value, which you would use as the index to the index into this hash table. So if I index into this entry, then I will look up, I will do matching to see if I match any of these entries. So I will do a sequential match. Okay, if here I match, then it's done. I find it. But if no match, it means cache miss. I don't find an entry here in the cache. Then I will look up the FIB table. Okay, so what happened is that if I send a 100 packet from X to B, X to Y, and with the router Z, okay, for the first, for those 100 packet, for the first packet, it would have what? Cache hit or cache miss. It would have cache miss, right? Then it would look up the FIB table, which we will see next. And then once it finds the entry in the FIB table, it would do what? It will come here to insert the entry into the cache. Okay, so I will take that entry and do the and take the destination IP address into the hash function, and then the result we use as the index into this table, and say here, okay, so I then traverse to the end, and I mount another new entry here. I will mount another new entry here, okay, to store the result I just found in the FIB table. Okay, so for the first packet, I would have cache miss. So I look up the FIB table, which would take a longer time, but eventually I got a result. And when I got a result, I insert into the cache. Okay, into the hash table, this hash table, so that the second packet and the third and the fourth packet would have what? Cache hit, right? They would have cache hit. So if I send 100 packets, the first packet would have cache miss, fine, but the remaining packet will be likely to have cache hit, so that they don't need to bother to look up the FIB table, which is large, but this cache table is smaller. However, if this cache entry, each of the entry here would have a timer, and they would expire. They will expire. So if I send 100 packets, but this 100 packets are not back to back, they might be far away, far apart. Then the cache, suppose I send 50 packets, and then I wait for a long time, and then send the next 50 packets. Then the cache entry here might time out, so that the 51st packet would have cache miss again, and then look up the FIB table again, and then insert into the cache table the cache, so that the 52nd packet would then have a cache hit again. So those entry here would have timeout value associated. And the reason you want to have timeout is because for the entry that are not used recently, they should be out. So that I can keep the table small, right? And if I keep the table small, then I would be fast in looking up the table. And consider a router, even though it might have packet destined to tens of thousands of destinations, but if you take a snapshot, say within 1 minute, most of the packet will be traversing to a small set of destinations. A small set of destinations. Or you take a 5 minute time interval, still you will see the set of destination is not too big, so that this cache table would not be too big. And how about the large FIB table? The large FIB table is an array of hash tables. But why? Let's look at the structure first. This is FIB table, and it points to this big hash table, and it's organized from by the prefix length. So if I have say 50,000 entries here in the routing table, so I would organize them according to the prefix length. So if I have entry which has prefix length of 32 bits, which is unlikely, I usually most of the prefix length will be between 16 and 24. 16 and 24. Most of the prefix length will be between 16 and 24. So I would have a lot of most of the entry here are null, meaning that they don't have routing table entries there. But you have most routing table entries distributed among a prefix length of 16 to 24. Okay. And then what you want to do is that, and then each of the entry will point to here an individual hash table. So I have a hash table here. This is a hash table, real hash table. But here is another hash table. So I have an array of hash tables. And the real hash table is here. And then it will point to a linked list here. So I have a linked list. This is FIB node, which is the same as this R table, which is in a linked list. Okay, the R table in the cache is essentially the same as FIB node here. Now here I have hash table entry here. Okay, so I'm organizing the routing table entry. I group them according to the prefix length. And as I said, most of them will be between 16 and 24. And all the other are likely to be null. And so now I want to do one thing. Why am I organizing? Why are we organizing into this array of hash tables? Why? And why are we ordering them according to the prefix length? Why? That's because we want to do longest prefix matching. And how do we guarantee that we will find the longest match? How? If I have this organization, how would I find the longest match? You start searching, or you start matching from what? The non-null or non-empty hash table, right? You start the longest. I mean you start the non-null longest prefix. You start from the non-null hash table with the longest prefix. So what you would do is this. I will start from here, 32, and this is null, fine, so I skip. 31, null. Until 24, it's non-null. So I do the matching here. So there's a hash table, just like this. There's a hash table, so I take the destination IP address and then feed into the hash function, and then take the result as an index into this hash table. And then I do the matching on the linked list. Okay. So if I go through this, I don't match. Then I do what? I do the next smaller, hash table with shorter prefix. So the 24 does not match. I mean 24, the prefix length of 24, no match in the hash table. Fine. I then match on the 23rd. Okay, so I work along this. So as long as it's non-null, I start from here, non-null, I do the matching, and eventually I will match. Eventually I will match. And I'm saying that the first match is going to be the longest match. The first match is going to be the longest. It's just like this. If you say, I want to marry the most beautiful girl I can collect, okay? Then what you would do is that you will take all the girls you know and then sorted them according to their beauty, and you put the most beautiful one on the first, and then the second most beautiful one. But again, those girls might not want you. So if the girl does not want you, then no match. But first of all, you sort them according to their beauty, and you do the match. You try to match with the first one. If no match, fine, you go for the second one. So essentially, it's this. You're organizing the prefix, the network prefix, into according to their length, prefix length, and you start from the longest one. So the first match is going to be the longest. So if you do that for your marriage, the first matched girlfriend is going to be the most beautiful one you can afford. Okay. So by this, that's you know the reason. You now know the reason why we are organizing this into an array of hash tables. That's because we want the first match to be the longest match. But again, you can see that I need to start from the longest non-empty hash tables, and it's most likely, okay, I say if the destination is in a network with a prefix length of 24, then what I would do is that I would need, and there are entries which are longer than 24, and I need to match with all of them, which is very troublesome, right? And it would take time. So I would avoid doing that. And the way to avoid looking up this FIB table is by the cache, which we have just seen. And by maintaining a small cache table, we could have fast lookup for most of the packets. And of course, there are flows, packet flows, which are short within just 1 or 2 packets. But most packet flows are long. For example, look up you send email, you browse the web page, and these are longer flows, but they are short flows. For example, you telnet, then your keystroke. Each of your keystroke might be 1 packet. Each keystroke might be 1 packet. Then and you might type slowly, so the flow won't be too long. And there are cases that are short flows, like for example the P2P. In P2P, when you send queries, you query a lot of people, a lot of hosts, and those queries are short queries, short flows, and then they are likely to. For those short flows, they are likely to have cache miss. most of them will cache miss. And then they will need to go through this FIB table. But for long flows, they would have cache miss on the first packet. But for the remaining packet, they will have cache hit. And they don't have to look up this FIB table. And this is so let's finish the open source implementation. And here you see the IP packet format that you would have many fields from the version, the header length, the type of service, packet length. You got header length and packet length, which kind of duplicate. The header length is only about a header, because the header is not fixed because of this, the options. You might have options. And then identifier that I uniquely identify a number for the packets, to identify the packets. And then that is used to detect duplicate packets. I mean the identifier. Okay, and then you got frag for fragmentation, and then a 13-bit fragmentation offset. And then time to live, TTL, which is not actually time, which is hop count. And at most, it will be 255 hops, meaning that the packet might traverse 250, at most 255 routers. But in general, it would the hop counts between crossed globally will be mostly 20 hops or 30 hops. 30 hops will be quite long already. So if you trace route from any two hosts on Earth, the likely number of hop count will be between 20 and 30. But if you trace route to some other host in Taiwan, it will be just less than 20. So within the country, it will be less than 20. But between internationally, it will be something between 20 to 30. And hop counts above 30 will be less often. So if I set a time TTL with a default value of say 55, it might be large enough. Anything beyond 55 is likely to have packet looping. If you have packet looping, and you might have more than 55 hops. And then upper layer protocol, it says this is a number saying what is inside this, the data. So I'm telling what kind of data I carry. And for this IP, I might be carrying TCP. So I have a number for TCP here. Or it might be UDP. So I have another number for UDP. It might be another IP packet. So I might have IP in IP. IP packet in an IP packet. Then this will be a number for IP. Okay, so this is a protocol number here, denoting what's inside my data. And then my header checksum will check just header, not the data. I just protect the data. I just check the header. And then source destination IP address, which each 32 bits, and then options. Okay, and as you will see that in IPv6, they remove this, no checksum. And they put this in the extension header, and then they take out the options into extension header too. So these and these are into the extension header. And then they take the identifier out, just like a checksum. They don't need it. Okay, but they add a floor number, so we'll see that they mostly simplify the header, IP header in IPv6, but in IPv4 it's like this. It's if it's IPv4, it will be, the number here will be 4. If it's 6, it will be 6 here. But again, the header checksum here is to check, is to to do error control on the headers, and I send it. If the receiver got the packet and find the header checksum is incorrect, if it's incorrect, then what? It would just simply drop it and doing nothing else. I would check whether the header is correct. If it's incorrect, then drop it. I don't do anything else. Do I? Yeah, bad IP header. If the checksum is incorrect, then I would send an ICMP message to the source, telling the source, okay, the header is incorrect. Okay, so I here just repeat what I just said. The version number, the header length. The header length is in units of 4 bytes. And then TOS. The type of service field mostly are not supported by routers. They are supposed to be supported by router, meaning if a router receive a packet, it should check the TOS, type of service field, and treat the packet differently according to TOS. But most router does not. Okay, most router does not treat the packet differently. Most router would just treat the packet equally, and without looking at the TOS. So IETF tried to redefine TOS by the so-called differentiated service call point, DSCP. And you will see that in Chapter 7. In Chapter 7, they try to use this field, DSCP, differentiated service call point, to differentiate packets, to differentiate the quality of service that the packet should receive. Okay, but still, even though IETF tried to redefine this to help providing QoS, but most routers still does not look at this and does not treat packet differently. Okay, packet length in bytes. The header length is in units of 4 bytes, but the packet length here is in units of 1 byte. And then identifier, the flag for fragmentation. So there'll be 2 bits in this flag. The first bit is do not fragment. The last bit, the second bit is more bit. So if I have this bit on, meaning 1, if this bit is 1, it means that the router should not fragment this packet. The router or the host should not fragment this packet. If the MTU of the link layer is too small to pass this packet, then drop it. Don't fragment, just drop it. Okay, this is do not fragment. And more bits stand for is this packet the final fragment? If it's 1, then it means that there are more packets. It's not the final packet, final fragment. There are more bits. So this is when a packet is jumped into fragment. and then say 3 fragments. Then the first fragment and the second fragment will have the more bits as 1, will have the more bits set on, but the third fragment will have the more bits set as 0, meaning there's no more fragment. So if you take this, well, let's look at the example later. And the fragmentation offset, if it's fragmented, then we need to denote the offset of this fragment. How far is it from the beginning of the first byte of the original packet? And it's in units of 8 bytes. And we'll see that with an example. TTL, again, it's not time, it's a hop count. And if TTL is counted, and every router, again, this is important, every router would decreases the TTL by 1. It would deduct by 1. So if I have a packet traversing 10 hops, then each router would deduct TTL by 1. And if TTL happens to reach 0, then this packet should be dropped. It should be dropped. And then the router should send an ICMP message to the source of the packet. Okay. And the upper layer protocol, which we have just mentioned, you will see the numbers for the protocol. Header checksum, that's a 16-bit ones complement, just protecting the header, including the options. Options here, you could have these options: source routing, loose and strict source routing, recall route, and recall timestamp. What is source routing? In most cases, every packet is routed hop by hop by each router. Each router just needs to decide who is the next router. It does not need to decide the entire path. However, if the source host, I'm a source router, or the source host want to decide the path beforehand, okay, there's an option for this. Okay, I can put the entire path that a packet should traverse into the option field. So I fill up the path into the option field. And with this, the intermediate router should do what? Should forward a packet according to the path in the option field instead of looking up the routing table. So I don't, in this case, then router just look at this option field and do the source routing, because the source has done the routing already. So I just need to follow the source, the instruction by the source, which is in the option field. So then I follow the instruction to forward the packet to the next router. Then I don't look up the routing table. And this is called strict source routing. Strict source routing. But there could be loose source routing, meaning I want to reach destination X, but before reaching X, please visit Y. Visit Y. So I'm here. Suppose I'm X, Y, and Z. So there could be a path. This is probably the shortest path. There should be a shortest path from X to Z. However, I have put a loose source routing saying that it should go to Y first before going to Z. it should go to Y first before going to Z. So I just put Y in the loose in the option field. Then the router between X and Y here should regard Y as the destination of this packet. So the router here, they would try to send the packet to Y. They would not take Z as the destination. They would take Y as the destination and send it to Y. And then Y, once it's reached, then it would try to, the router here would try to reach the destination Z. And that's loose source routing. How about record route and record timestamp? It said with this option, you can ask the intermediate routers, router in between, to timestamp and to record themselves. They can stamp their ID, their address, and they can stamp the time passing through them. See, in the header, the destination is still Z, for example, and source is Y and X. But in the option field, there's a format. There's a format for how you write the address for Y and also for entire path, if you like. If you need to put an entire path, there's a format for that. And there's a format to indicate this is the strict source routing or loose source routing. And it's in binary form to represent that. Okay, and if you have this option, the routers are supposed to handle the packet differently. Okay. But unfortunately, I think I remember that 10 years ago, most routers still, with these options enabled, meaning they are configured to handle packet with these options. But recently, due to the security reason, because with this you might have DOS attack on routers. So many routers disable the options, meaning if you have packet with this option, they ignore. They would not do source routing for you. They would not do timestamp for you. So they might be disabled in some router due to the security reasons.